Good morning, everybody.
Good morning.
I'm starting the streaming on the channel YouTube. Good morning, everybody.
Good morning.
Do you have the opportunity of looking at the streams on the channel? Does it work? Can you see the lectures? In particular, the first lecture we held on Tuesday. I hope it
Yeah.
can. Okay. Please note that the calendar of the class has slightly changed. In particular, we have moved one of the seminars on MATLAB of 1 week. We have postponed one of the seminars of 1 week, so please download the updated calendar. Then I shall tell you that I have reserved the P28 lab room, il laboratorio del Pineca, P28 for the MATLAB lectures. This means that MATLAB lectures will be held in presence with Alberto Barause in Pineca. È chiaro per tutti?
Yes, it's clear.
Okay. This means that those dates that you will find on the calendar, you shall go to the Pineca room. That is in the, I think, in Sotterraneo, below ground room in the department of, which is that department? It's not industrial engineering, instead it is environmental, it is ingegneria civile, edile e ambientale, licea. So you may join this room passing from Via Luzzati. I'm saying this for the Erasmus students because I think Italian students know very well where to go. Apart from that, I'm looking at the list and I see that today there are only 3 Erasmus students. Erasmus students, can you raise your hand so I can check that you are really 3 or maybe 4? Okay. Mademoiselle Acuna?
Yes.
Yes. I already told you the history of Tristan da Cunha, right?
Yeah.
It's very nice, that history. Okay, at the moment being, I see only 1 resident, so to my understanding, there is only 1 Erasmus student. But there are some foreign students whatsoever, so I will, of course, speak English. So today we shall introduce some epistemological, or if you want, physiological point of view perspectives dealing with ecosystems. As you will see, modern science, modern ecologists feel the need of changing a little bit, or if you want, changing significantly the perspective, switching from a reductionistic perspective, that is that of a classical physics or mechanics, if you want, it is the Cartesian science, Cartesian reductionist science. And the sentence that may summarize up the concept of reductionism is that the whole is equal to the sum of the parts. You should note that classical scientific models are all based on simplification, but appear to be necessary to reduce the computational demand. But this often make the model unrealistic, and this is terribly true in ecosystem modelings. But to stay on the classics, it is also true for quantum mechanics. I call you that one of the 6 fundamental principles of quantum mechanics is the Heisenberg principle that I have summarized here, written here. In this principle says that the uncertainty on moment multiply on the uncertainty of the position of an object is always greater than, even if a small constant h, but h is the Planck constant. And this is a way to formalize the fact that in quantum mechanics, it appears clear and it becomes a postulate of the science itself, but if you increase, you cannot increase arbitrarily knowledge about a system, because in particular, if you increase the detail in which you describe the position x of a particle, then you will have to decrease the precision by which you describe the speed of a particle. P represents a quantità di moto. How do you say in English? Momentum, if I'm not wrong. This means that P, it is linearly dependent on the speed. This inequality tells you that if you reduce the uncertainty on the position, then the uncertainty of the speed has to grow, and the limit is given by this physical limit, that is Planck H constant. This is, if you want, immediate consequence of a reductionistic approach, Cartesian approach on mechanical systems. And we discover that in quantum mechanics, this is not acceptable anymore. And I will try to explain to you today that also in ecology, we are in a similar position. This is not acceptable anymore. So modern ecological science tends to change its perspective, and this is an epistemological change from reductionism to holism. The concept of holism may be summarized by the sentence, the whole is greater than the sum of the parts. This perspective, this paradigm, requires a systemic approach and entails with it some, if you want, weird concepts like that of chaotic systems. And this, as a consequence, the fact that the estimates in the long term are practically impossible. We can never know the world with an arbitrary accuracy. And the point is that we must accept the condition of the new science. So when we focus on ecosystems, we are limited epistemologically by these considerations. And now, today, I will try to explain you why this is necessary when dealing with living systems. In the holistic perspective, we may say that most systems in nature are inherently irreducible, meaning that you cannot compose. It is not always possible to interpret observation of a system operation through the observation or through basic principle, or through the observation of the components of the behavior of the components of a great system. So this is why, especially in ecosystem theory, we need to resort to empirical models in order to improve our knowledge of the behavior of a system. By this schema, I try to explain how ecosystem theories try to interpret the reality through the application of models. So the idea is we try to conceptualize the behaviors of a system by building a mathematical model. Then we pose some questions concerning the behavior of real systems for a model, the questions may get an answer through simulation. Why, once we have built a satisfactory loop linking model and reality, so model, I pose some questions, and then I have the answer through simulation. So I'm ready to employ this tool for scientific inquiry, and I'm ready to pass from simulation with a restricted validity to theorization with general validity. This is to explain to you that this way of describing reality, what is an holistic approach through models, may also be employed to infer theoretical aspects, so may also be employed to study and to deepen our understanding concerning the theory of ecological systems. So, how we may interpret the reality through modeling? We recognize that experimental observation do not produce new laws, but instead, empirical or experimental observation results in a new model of a specific part of a reality. You may recall I have already introduced this concept on Tuesday. Ecological modelers build a model with a specific view, a specific scope, that is that of simulating some specific aspects of a reality. So we are not pretending to simulate the whole system. Instead, we simulate some aspects of the system that we think that may be of relevance or may be important to understand in order to understand the behavior of the system. So a new model of a part of reality. The practice of modeling of environmental system is today possible thanks to recent developments in ecological theory, what we are talking today. So changing the perspective from a reductionistic to a holistic view, and thanks also to the increase in computing powers. So for the fact that we have PCs, and in our PCs we may build some caricatures of a reality, of a real systems or real ecosystem. And by these caricatures, we may run a model and we may obtain some answers concerning the behavior of a system. So ecology, theoretical development, and technical development related to computing. So how may we see the new paradigm? The new paradigm is an interplay between analysis and synthesis. Analysis, that is observation. If you want, it is not enough to understand the enormous complexity of ecological systems. Instead, the new analytical results may be used for the formulation of the synthesis. The synthesis is necessary to investigate the emergent properties of a system. The synthesis in our language, so the model, indicates what new analysis may be required. So you see that analysis, observation, and synthesis, models of real system, play together in a kind of circular or cyclic approach, passing from analysis to synthesis. So observation, modeling the observation, the model may suggest a new observation, so we improve the analysis and we change the synthesis, improving the models and so on. This is an iterative process that somehow describes the paradigm of ecological modeling. But why we are making all this speech? Why we are making all this discussion? Because we realize the fact that we may say the world equation does not exist and nature is simply too complex. It performs non-linear behaviors, may appear chaotic or catastrophic, and some weird effects appear like that of a sensitivity to initial conditions, the well-known butterfly effect you may already have heard about, meaning that in such complex systems, the initial conditions are so, the changing of initial condition may end up in dramatical changes of the final effects. For example, a butterfly flying in New York may generate a tornado in Tokyo. Of course, in the laboratory, everything is much easier. In the laboratory, we may control at least external physical-chemical conditions, and this allows us to concentrate more on those aspects related to biological processes. Now, we should go a little bit more in detail in describing how this new paradigm may be implemented. In order to do so, it is important to start by making some observation on ecosystems or living objects. Now, you will learn by my lecture that I'm often confusing ecosystem and living objects, because ecosystem, in my view, are the prototype of a living object. If said in other words, I can say it in a worst way, and it is that we may say that the observation of a living system is always linked to the fact that this system is in fact living, so it may perform unexpected response to external stimulations. The reductionistic paradigm says that if you want to understand how a complex system works, you may or you should understand how the composing parts of the complex system work. This is as to say that if I want to understand how a complex system functions, then I have to compose this complex system into subsystems, and then I have to understand how this subsystem works in order to gather a comprehension or an understanding of how the whole large system works. The epistemological shift we are talking about today tells us that this is not the case, meaning that even if we understand the working of a single part making up the complex large system, then it is not at all certain that I will have an understanding of the working of the behaviors of a larger system. Why this? Because living system or ecosystem, ecological system, living, etc., by perform or manifest a strange behavior that is called, maybe referred to as emergent properties. There are some properties that are typical or specific to the larger ecosystem, and that cannot be simply reduced by the analysis of the parts composing up the system. The typical example I make here is that of a cat, meow, the animal cat. If you want to understand a cat, to understand how the machinery of a cat works, the reductionistic paradigm tells you that you have to open the cat and analyze all the working of single subsystems making up the cat, for example, the liver, the glands, the lungs, the muscular system, the skeletons, neurological system, and so on. But when you have gathered a perfect understanding of the physiology of the cat, but at this point you have a big problem that the cat is dead, because in order to understand the behavior of a single part of a cat, you have to open the cat and to disassemble the cat and to, according to the reductionistic paradigm, to understand the working of single systems of a cat. But when you do not have a living cat anymore, this is typical for living system. You cannot imagine to understand the working of an ecosystem by simply understanding the working of all the parts composing up the ecosystem, because a typical characteristics of living system is that of displaying emergent properties, so that the whole system manifests some behaviors that are not directly predictable by the understanding of the working of a single subsystem. Now let's give a look more in detail on how we can define the ecosystems as an object of our research. First of all, we may realize that ecosystems display a specific level of organization. As we have already said on Tuesday, building of a description of an ecosystem requires the establishment of scales. In particular, we need to select appropriate spatial and temporal scales. And this has to do with a specific level of organization of system. We will try to be more clear in that later. In order to understand what we mean by this sentence, it is useful to go back to some of the classical definitions of ecosystems given by ecologists, in particular Morowitz in 1968 said that ecosystems sustain life consistently to the actual condition. So Morowitz recognized that probably the most important aspect of living system, of ecosystems, is that of being arranged in order to foster, to sustain life. So it looks like a matter of kind of auto-referential, self-referential definition. But instead, the concept here is that we recognize that the ability of sustaining life is a property of entire system rather than of individual species or population or subsystem that constitutes the whole system. So the first emergent property we may recognize is that ecosystems are so structured so that life or living subjects appearing to the plot are sustained by the ecosystem itself. This is the definition of Morowitz in 1968, who started to look at the ecosystem as object made able to sustain living system. Please note that ecosystems sustain life consistently to the actual conditions. This means that ecosystems are objects that accord or register consistently to the actual conditions and in some way buffers external perturbations in order to maintain the local conditions of a system suitable for life. It is a, please remember, this is a property of entire system and not a property of various sub-elements constituting the system. In my view, in the view of the ecologists, sub-elements may be individual species or population, and so on. We shall go 10 years back and look at the definition given by Ipiodum in 1953. Ipiodum was really one of the fathers of the science of ecosystem theories. Ipiodum, that was a physical chemist, and proposed a definition that is the one that we prefer most. An ecosystem is the set of physical, chemical, biological activities in a confined spatial-temporal unit. Please note, we are talking about physical, chemical, and biological activities, but we are also talking about a confined spatial-temporal unit. So you may remember, we have just said that the description of ecosystem requires the selection of appropriate spatial and temporal scales. And for this was already clear to Odom 10 years before, because Odom recognized that one of principal characteristics of this ecosystem, besides that of sustaining life, is that of maintaining locally stable conditions for the thriving of living system. We may say, recast the definition of Odom by saying that an ecosystem is a unit, or if you want, functional biotic system. Unit means a well-defined portion of space and time, so spatial temporal unit, that sustains life, includes all biotic and non-biotic components, and already Odom in 53 recognized that the scale are not defined a priori. Instead, the scale depend on the objective of the study. So the scales are somehow defined by the observer, because it is the observer that decides which is the focus of the model. So decide, for example, if we are looking at chemical processes, then our spatial scale will be that of centimeters or maybe millimeters, and the temporal scale will be that of seconds, minutes, and some hours. If we change our perspective, for example, on landscape processes, then the scales, the spatial scales will be that of kilometers or hectares or hundreds of meters, and the temporal scales will be that of weeks, months, seasons, years, or decades. The other non-trivial observation made by E.P. Odom in 1953 is that living systems manifest two show two quite strange or weird properties. The first one is one of being complex system, and as I told you on Tuesday, complex means embracing different hierarchical levels, so embracing several scales. And the other non-trivial or new characteristic is that of being able of self-organizing. Self-organization meaning responding in non-trivial way to external stimulation. This is self-organization. So complex systems like living systems may change their behavior in a non-trivial way, and by ecologists is self-organization. I am schematic, so I try to draw schemas describing the structure of ecosystem. So let's, to summarize, to draw a summary of all these blah, blah, blah we have done up to now. And in order to be the most clear as possible, I try to schematize these by drawings. So I propose this schematic description of the structure of ecosystem. First of all, we realize that ecosystems are open systems in which you have a boundary, that is the dotted line here, that separates an internal part of the ecosystem itself from an external environment. This separation is not neat. Instead, there is a continuous interaction between external environment and the internal part of the system. The interaction is carried by energy or matter flows. So we have a neat energy, matter flows entering into the system. Typically, the energy in this case is solar radiation, because solar radiation is the basic for primary productions, as we will see soon. So the energetical basis is that of sunlight coming into the system, and the ecosystem, while it is working or performing, it is interacting with the external environment by, for example, throwing, again, energy, but in this case, in the form of thermal radiation. So an immediate observation is that we have a high quality energy entering into the system, solar radiation, light, that is somehow degraded to thermal radiation, and it is remitted to the system. Why do we think, or we say that solar radiation is a higher quality radiation? Because solar radiation is, how to say, very well defined in space. You can identify a locus through which sun energy flows, while thermal radiation, it is molecular vibration, it is diffused energy. From an engineeristic point of view, we may say that solar radiation is much easier to be transformed into useful work, while thermal radiation, it is much more difficult to concentrate thermal radiation and produce work, while it is much more straightforward converting solar radiation into some other forms of energy. Please note that besides the flow of energies, we have also flow of matter. Material that is entering the system. Typically, we talk about nutrients that are essential for biochemical synthesis. But on the other hand, we have also a bypass product of molecular metabolism in the form of wastes, again, matter, for example, use urine, feces, and so on, that are re-emitted through the external environment. So if we describe an ecosystem, living system, the first thing we recognize it is the existence of a boundary, a border, that distinguishes an inside from an outside. The inside is a controlled environment, controlled in the sense that it buffers the perturbation coming from the external uncontrolled environment. So I think by this perspective, it may come to you the idea, the schematization may explain you what we meant by the idea of locally decreasing perturbations and constructing buffer systems that may absorb external perturbations, so that we may distinguish an external environment that is terribly perturbed from an internal environment which is, on the other side, stable. Then, once we go into the details of what's going on inside the ecosystem, then we may recognize two general categories of elements: abiotic components and biotic components. Abiotic components are typically physical, chemical, climate, but also geomorphology, but also hydrology. Biotic components instead are, from the ecologist point of view, communities, populations, communities of population, population of organisms, and at the lower hierarchical level, we may say bacteria, that is the smallest living object we may individuate today. The processes linking the working of biotic components are called biochemical processes. On the contrary, the processes linking the abiotic components are chemical physical processes, so chemical reactions or changement of phases, thermodynamic processes, if you want. Of course, chemical processes and biochemical processes are linked in a non-trivial way. So, the fact of building an ecological model or the model of an ecosystem is redefined here on the fact of building mathematical model of abiotic components, mathematical model of the biotic components, and will localize spatially and temporally these models into a well-defined spatial-temporal unit. The concept of cycling is very important here. You may recall one popular way of defining the principle of energy conservation. Energy is nor created nor destroyed, instead it is transformed. In order to explain how this energy is transformed, we shall include in our description of living system what it is called nutrient cycling. In particular, internal nutrient cycling, as we will see in several examples, is an important characteristic of living system, and it is very unlikely, but you may be able to build a meaningful ecosystem model without including some kind of internal nutrient cycling. There will be several ways of looking at this concept. We will talk about limited and unlimited growth. We will say that unlimited growth is ecological nonsense. So growth, biologically speaking, cannot be foreseen as unlimited because the resources are limited. And these entangles as a consequence the fact that nutrients have to be recycled, because nutrients are the elementary components, atoms, if you want, that make up biological matter. So internal nutrient cycling is a key aspect of an ecosystem works. So how, to summarize, how are we looking at system? The ecosystem is an object of research. Empirical studies trying to assemble pieces of knowledge into an organic description. This is what we have called the analysis. Comparative studies, some functional and structural units of different ecosystems display a similar performance. For example, the process of respiration, it is a functional process that is common to several living objects, and it is maybe found in several structural units of different ecosystems. So there are some processes like respirations or exudations, or we'll see many examples of this, but are prototypical, so are important to be studied in an analytical way. Then we have experimental studies that consist in this ambit as a manipulation of the entire system in an attempt to grasp the relevant properties with the typical scientific approach. And then, because we deal with very complex systems that are inherently irreducible and should be looked at by an holistic perspective, we need the modeling or the synthesis or computer simulation. All these four approaches are needed in order to obtain an adequate holistic description of such system. So if you want to build an holistic description of a living system, then you will have to resort to empirical studies, in which you look at simple aspects or pieces of knowledge into an organic description. Then you do comparative studies, so you recognize that some of the processes you were looking in the first phase, in the first approach, are common, ubiquitary to several systems, living systems. For example, the example of respiration process is just a process of oxidation of organic matter. Then you may resort to experimental studies, and this is particularly important to environmental engineer that tries to control the system. I recall you that the name of this class is modeling and control of environmental system. So the idea is that of controlling, changing the behavior. And the last aspect is that of modeling or computer simulation, but help us in sort out an analysis, sorry, a synthesis from all the analytic work that has been done before. Let's give more a look in detail to some of these weird concepts that we have introduced this morning. And let's try to place it in the right epistemological context. First of all, we recognize that living system may be to some extent ordered or / disordered system. Order and disorder is a concept that is strictly connected to the concept of information. Ordered system in general, we may say, they contain much information, but disordered system. The other concept we have introduced here and there in these two lectures is that of complexity. We are dealing with complex systems that are acting at different hierarchical levels. And so you may not expect to understand the behavior of the system by focusing only on a specific hierarchical level, but instead you shall give a look also to a neighbors level, hierarchical level. So maybe one hierarchy lower or one hierarchy upper. Okay, I understand this maybe may sound a little bit foggy, but I will try to give you some example of this later this week. The other concept is that of random and chaos. We have seen that somehow linked to the concept of order and disorder, there is also the concept of randomness and chaotic behavior. And we have also talked about the self-organization capability of this system. So this meaning that these systems are able to reorganize and to change their behavior in order to perform non-trivial tasks. In order to put all these concepts in a common framework, I tried to make a sketch. You know, I am a schematic, a sketch. For example, I put on a horizontal axis an indicator linked describing the order or the disorder of a system, while on the vertical axis, I put an indicator related to complexity. Order and disorder for me, but I'm a physicist, it is quite easy to measure. It is related, as you can imagine, to a concept of entropy. Disordered systems are systems that display a higher level of entropy, while ordered systems display a lower level of entropy. But the impressing point is that between these extreme order and disorder, the living system place themselves some how in between. And we call this system self or auto-organizing capable systems. To give you an example, let's think at a very well-ordered system like a crystal, for example, carbon crystal, diamond. Would you say that this system is complex? I would say no. It is a very highly ordered system in which, if you may recall the Bravais reticule, you may describe each crystal by 3, 4, 5 numbers, i reticoli di Bravais. So a crystal that is a highly ordered system for sure is not a complex system. This is why complexity for this system starts in 0 here. Let's instead think to another completely disordered systems, like for example, the explosion of TNT, nitroglycerin, or the explosion of dynamite. In the specific locus of explosion, you would say that the disorder is maximum, because you have a lot of a complete spectrum of locations and velocities of the particles making up the system that has exploded. I wouldn't say that an explosive system is a complex system. Instead, it's a system with a very low complexity. Then living system are in between maximum order and maximum disorder are those systems that are able to self-organize, to respond in non-trivial way to external perturbation. And so these are the systems that I would, or we ecologists would call complex systems. So are those systems that display the maximum level of complexity. Okay, am I too exotic? Or can you follow my reasoning? Can you see what is the perspective of theoretical ecologists now? Does this tell you something about what we mean by self-organizing complex system? I hope this may shed some light on this. Now, let's finish the lecture of today by giving a look on how the most engineeristic and holistic approach, scientific approach, that is that of thermodynamics, may tell us concerning ecosystem. From a thermodynamical point of view, first of all, we recognize that ecosystems are open systems. You remember? Open to flows of matter and energy. So these are open systems in which something's come in and something goes out. This is completely different from the thermodynamical concept of closed systems in which nothing can enter and nothing can exist. But from a thermodynamic point of view, the more striking aspect of this system is that these are systems that are far from the thermodynamic equilibrium. What does this mean? What is thermodynamic equilibrium? You may recall that there are several definitions, but the thermodynamic equilibrium sometimes is referred to as the thermal death. Thermal death. So when a system is dead, it goes toward thermodynamic equilibrium. So living systems are systems that are not in thermodynamic equilibrium. Of course, they are not because they are crossed, because they are open systems, they are crossed by flows of matter and energy. They transform energy. Solar energy becomes thermical energy, so infrared. So we switch. There's a passage from light to infrared radiation. They are also changing material, transforming matter. nutrients, elementary elements like nitrogen, phosphorus, carbon, hydrogen, and whatever, silicates, and so on, are transformed into organic matter, biomass. In order to do this system are far from equilibrium. Where we would call this state a steady state, probably, but anyhow, far from the thermodynamic death. And in doing this, from a thermodynamic point of view, they perform a process of energy dissipation. What is energy? When I say energy dissipation, I'm thinking of the fact that solar energy, that is a highly ordered, coherent form of energy, is transformed into thermal energy. It is highly incoherent, diffused form of energy. From the coherent, ordered form of energy, light, we can extract useful work. It is much more difficult or much more cumbersome to extract useful work from thermal energy. Another important aspect that emerges from the thermodynamic approach, holistic approach to ecosystem, is that this system seems to accumulate locally order, or if you want now, information. Why I am saying this? This is in front of you in everyday life. For example, you may look outside your window now and you see a tree in the garden. You will notice that the tree is made up of some very well-defined structures or functional units or functional processes. For example, trees have leaves, or the leaves are the same structure. So that, like in the case of crystal, you may recognize the fact that when life is at play, then locally there is some kind of information that is accumulated. Somehow, you may say that there is some kind of order that is appearing as an emergent properties. Living systems, from a thermodynamic holistic perspective, accumulate order locally. But also, we shall recognize that there is a kind of energy transformation. And in particular, ecologists tend to switch their perspective from the quantity of energy that is processed to the quality of the energy produced. As we will try to say and to make clear several times, ecologists recognize that there are different qualities of energy. Different qualities of energies may be the same quantity of energy, may be related to different qualities. Example, you shall agree with me that 1 kilogram of the meat of a cow contains an energy that, in terms of quality, is different from 1 kilogram of biomass of grass. Grass is primary production, so what appears from the direct transformation of light and elementary materials like nutrients into biomass. So the first step of transformation is that of primary production, grass. Then we have a further step of transformation, that is the herbivore that is feeding on grass and is transforming this energy, same quantity, into different qualities of energy. So the energy stored into meat of a cow. Of course, this is, to dietologists, this is a well-known condition, well-known aspect. The other important characteristics of ecosystem from a thermodynamic point of view is that these systems tend to grow. Growth In this context means accumulation of biomass, but also increase of flows. However, as we will say several times, this growth process is not unlimited. Instead, it is limited by the availability of resources. But the more striking, if you want, aspect of ecosystem is that besides growing, this system tend to develop, so tend to undergo structural changes. This in a thermodynamic or holistic perspective may be called development. From the perspective of an ecologist this is called evolution. Evolution is the changement of living structures through different development stages, so that living structures undergo structural changes while they are growing and while they are crossed by a continuous flow of energy matter that these flows maintain the system, the living system, in a far from equilibrium conditions. In this condition, this living system dissipates energy, transforms solar energy into thermal energy, accumulate order, information by building biological structures, and they transform the quality. They transform some quantities of energy into different quantities of energy of a different quality. Okay, is this clear? Do you have any doubts, concerns, questions? Are you following my way of reasoning? I hope so. Okay. It is very important now to switch our focus onto the concept of energy flows at the level of a biosphere. We said that from a thermodynamic point of view, ecosystems are open systems, open to the flow of energy at least, but in particular, we may say that they are also closed to the flow of matter. The concept here to keep in mind is that these systems are continuously transversed by energy and matter. They are open to energy flows, closed to matter flows. In anyhow, they kind of steady equilibrium. Sorry, when I say that these systems are closed systems, in this context, is that I am, let's see if I can make a sketch. Closed systems, because we are talking about a biosphere. So we may consider the biosphere as a whole as a closed system. The biosphere is in steady equilibrium. Inside this closed system, the biosphere, there are several open systems that are the ecosystems. So if I look at the biosphere as a whole, I shall consider this system as a closed system in terms of the flow of matters, and an open system, but in steady state in terms of a flow of energy. So the energy flows is that of the sun, the energy, solar energy is that, but is the energy, but it is keeping the system in a far from equilibrium condition, but in a steady state equilibrium. The stability of a system is maintained by dissipative processes of a degradation of energy, transformation of light into thermal energy. So degradation of solar energy is the process that maintains the stability of the biosphere. But from a thermodynamic point of view, may be seen as a closed system. Closed to matter flows, of course. The matter that enters into the biosphere is that of cosmic matter, like meteorites, or so it is really neglectable. Instead, the energy that is crossing the system is not neglectable at all. Instead, it is solar energy incoming, solar energy input, and thermal energy output. It is this flow that maintains the stability through degradation processes. So we may look at the Earth as a thermal machine, and it is this thermal machine that generates and regulates the climate. The climate on the whole surface of the planet is stabilized by the so-called Hadley cells. Hadley cells are convective cells that are built up between the equatorial latitude and the tropical latitude. In the northern hemisphere, the Hadley cells are clockwise, while in the southern hemisphere, the Hadley cells are counterclockwise, convection cells. So we have two enormous convective structures, one in the northern hemisphere and one in the southern hemisphere. You can imagine that solar light arrives perpendicular at the equator. So this is why we have the most impressive or most significant accumulation of energy built up with two convective cells. The interesting aspect of the Earth's thermal machine that regulates the climate, that is made up of these two gigantic convective cells, is that the temperature all over the planet is maintained at an average of 287 Kelvin degrees. And this average is obtained on the whole surface of a biosphere and on the whole yearly cycle. So it is an average in space and time. If you convert this figure 287 Kelvin into Celsius, you obtain the figure of 14 Celsius degrees. That is the average temperature on our planet all over the year and in every place of the planet. For example, if you dig a hole after some meters of depth, you will find that the temperature in the upper part of the crust, so in the biospheric base, if you want, is 14 Celsius degrees. This figure appears everywhere, 14 Celsius degrees. How these energy flows, how can we evaluate these energy flows? We start by employing the solar constant, what is 1,360 watts per square meters. So it is a density of energy flow. Watt, I recall you, are joules per second, so it is an energy flow. If you divide per square meter, it is a density of energy flow. And the solar constant, this figure, 1,360, but it's today's value of the solar constant, is that measured at the intermediate distance, Sun, Earth. And the solar constant, it is a characteristic of the actual performance of behavior of the solar machine. I recall you that the solar machine is a gigantic atomic central in which you have nuclear fusions. The energy is produced by nuclear fusion. Of this energy, we recognize that 9% is in the ultraviolet, 41% is in the visible, while the half, 50%, is in the infrared. So these are the composition of solar light that arrives on the surface of our planet. The surface receives directly 26%, indirectly 25% of this energy. The ultraviolet radiation is almost totally absorbed in the higher part of the atmosphere, that is the stratosphere, while infrared radiation is absorbed at the troposphere level, that is the first 10 kilometers, and the infrared radiation is absorbed by CO2 and not to and so gases such as this. And this is the so-called greenhouse effect. I have tried to schematize these flows by this drawing. If we make 100 incident solar radiation, of which 100%, 35 is immediately reflected by dust, gas clouds, and albedo. Of 65%, 19% is of the remaining 65%, 90% is absorbed by atmospheric gases like ozone, steam, clouds, and so on. And 46% is absorbed by the Earth directly or indirectly. Of these 46% of energy, only 5% is that responsible for the atmospheric circulation. So this includes heat of evaporation, convection, and so on. So you see, it is very low quantity of this energy that is responsible for the Earth climatic machine. The important thing is that of these 46% absorbed, the same exactly 46% is re-irradiated by the Earth. The atmosphere re-irradiates 19%, so that in the end, we have exactly a balanced quantity. What it arrives onto the surface of the planet in terms of energy is what it is re-emitted by the planet itself. So this is what we mean by being in a steady state condition. The biosphere, of course, is open to the flows of these energies, but through these flows, it maintains a kind of steady state condition. So now we are forced, and we go little by little to biological processes, we are forced to try to analyze how these energetic transfers in the biosphere take place or may be described. We may convert the solar constant 1,360 watt per square meters into kilocalories per year. So here we are making an integral on the surface and on the year, and we obtain a figure of 1.2 10 to the 22 kilocalories per year that are directly incident on the surface of the planet. This energy is coming from the sun. Of this energy, terrestrial vegetation and phytoplankton, what we will subsequently call primary production, primary in the sense that they convert directly solar energy into biomass. Terrestrial vegetation phytoplankton use of these 10 to the 22, 2.5 10 to the 20 kilocalories per year to live, and of this they produce 5.2 10 to the 70 kilocalories per year of new biomass. If you make the ratio between what it is used and what it is produced, you obtain an efficiency level of 0.2% of transformation. So the primary production has a very low efficiency of transformation 0.2% of the energy that is employed by the primary production is transformed into new biomass. So this is a figure that gives you an idea of the efficiency of the primary production. If you look at in terms of different traffic levels, you may say that the light that is arriving on the surface of the planet is transformed with an efficiency of 0.2% into primary production biomass. But then we know that on the biosphere that this biomass produced is employed by upper traffic level to produce other different types of biomass. Again, energies with different qualities. Do you remember? The subsequent step of transformation, that going from primary production to herbivores, has a much higher efficiency, 3%. Our cows are very well working machinery in terms of producing meat on the basis of primary production, 3%. And then when we go to upper traffic levels, it is that of carnivores essentially, or those animals consuming the biomass of herbivores, they may display much higher efficiencies, up to 40% efficiencies of transformation. So this cascading schema describes you the fact that to an increased quantity of energy coming from the sun in form of light, it corresponds to a chain of transformation, an increased or a lower quantity of energy, but of a higher quality, a lower quantity of energy of a different type. So which bring us to notice that we may associate some quantities of energy to the biomass. So if we look at the process of production, what in terms of biochemical transformation is called photosynthesis, the transformation of solar energy into energy stored into the biomass. This is primary production, synthesis of organic molecules, and then the complementary process of production is that of consumption. In terms of biochemical reaction, we call these processes fermentation or respiration. These are both oxidation processes. During the processes of consumption, so oxidation of biomass, the ATP, adenine triphosphate molecule, is produced, but is the fuel for all cellular processes. You may recall from your chemistry classes, especially high school, I don't know, the university, if you do some kind of biochemistry. I think so in the beginning of your career. ATP is a molecule that transports the energy obtained by fermentation and respiration, so transformation of production into useful energy for the cellular processes. We shall notice that all the biomass has a more or less fixed stoichiometric structure, so that we may find some kind of conversion factors telling us how much energy per unit mass is contained into different types of biomass. In particular, plants contain 19.2 kilojoules per grams, algae 21.3 kilojoules per grams, while invertebrates 23 and vertebrates 26.3. You may, due to the fixed stoichiometry, read these figures also in terms of different biological molecules or biological products. Like, for example, carbohydrates, proteins, and lipids, they have a different energy content, 16.7 kilojoule per gram for carbohydrates, 20 kilojoule per grams for proteins, and 37.6 kilojoule per grams for lipids. So, of course, the lipids, as people who undergo diets knows very well, are those who contains the largest quantity of energy. Okay, if you don't mind, I would like to stop my lecture here, and we'll get back next week on Tuesday with a brief history of the biosphere, and by which we shall continue our description of the ecosystem as an object of research. Okay, I stop here. I stay in the class for some moments. If you would like to pose some questions, I'm here. Please don't hesitate to pose questions.